this is another issue which we should know, how the heat transfer varies along the mold depth. This is distance from the top of the mold. You possibly you know that within the mold, just look at the meniscus is just not at the top of the mold. Please try to understand why it is not so, because otherwise there may be, even when there is a oscillation, this liquid steel everything might come out. So, that is not desirable. So, this meniscus level is at certain depth from the mold top. So when in that figure I will show the mold top, that means that this position is the 0 and we are coming down the mold. So, this is what is important. So, along the mold depth how the heat transfer is changing, that is what we want to show here. So, this was the mold top. So, the meniscus level is somewhere here, this is the meniscus. It is not at 0 position, it is certain at a depth, say maybe 70 millimeter or so. This is in millimeter distance from top of mold. So, at the meniscus level, what is happening. That means the heat transfer is trying here, that is this is basically heat transfer along mold depth and heat transfer, the horizontal heat transfer. That means how the heat is extracted from molten steel to the mold. I am talking of that heat transfer, it is not a vertical heat transfer. In the mold is the mold top, so it is the away across the mold I am talking of this heat transfer. So, this heat transfer is somewhere trying to increase here and it is at a peak at a certain depth from the meniscus. Why? Because at the meniscus what do you have? It is just the shell is trying to form. If the shell is very thin, there might be some contraction. So, that means there will be air gap. So, air gap controls the heat transfer. So, the peak of the heat transfer is at a certain distance from the meniscus, maybe 30 millimeters. So, maybe at a depth of 100 millimeter from the top of the mold. So, from the meniscus is around maybe 30 millimeter. So, the peak of the heat transfer is somewhere here. Then what it has shown, it is showing is two different steel, one is a 0.7% carbon and it is a 0.1% carbon. As I was telling you, the steel grade plays a very important role in heat transfer. This slowly you will try to understand why it happens. So, 0.1% carbon, if you look at it, the heat transfer is relatively less. Not only the peak of the heat transfer also, but along the mold also it is relatively less compared to 0.7% carbon. Why it is so, you will understand later, but I am just giving you a hint. 0.1% carbon is a depression type of grade. That means the surface you get lot of depression, and 0.7% carbon, it is not a depression type of grade, because of some other reason, I will come to it later, there is a mode of sticking. So, you have the shell trying to move towards the mold. So, there is hardly any gap between the mold and the shell except the gap of the slag layer. So, that is why relatively you have more heat transfer per 0.7% carbon. In fact, if you plot the similar curve for say 0.02 or 0.03, very low carbon, it is similar to 0.7% carbon, because there also the shell will not be, will try to stick towards the mold. So, the heat transfer will be more relatively compared to 0.1%. 0.1% carbon, that is we call it a peritectic. If you remember, the peritectic reaction starts at 0.1% carbon. So, this 0.1% carbon is called the peritectic composition, though it is just the beginning of the peritectic reaction, but it is called peritectic composition because of some other reason. I will come to it later on, because this particular composition around 0.1% carbon will be having lot of surface defects called depressions. So, that is why the heat transfer is relatively low for 0.1% carbon. And why this heat transfer comes down along the mold? Because as the shells becoming more and more thick, naturally there is some less amount of heat transfer is needed, number 1. Number 2, the heat transfer also gets a lot of resistance because of the thicker shell. Number 3 is, as the shell is increasing, there is a more probability of the shell getting contracted. So, that is why also there will be some air gap formation. So, all these factors will lead to the heat transfer coming down from the top of the mold to below the mold. Finally, when you are coming out of the mold, then it is no longer the heat transfer in the mold, but that is a different, this is called secondary heat transfer. The heat transfer there is still less, because more thick shell has formed. So, naturally you do not require so much of heat transfer. The heat required to be transferred from the inside, the liquid pool comes down. So, this is very important. The heat transfer variation from the top of the mold to the bottom of the mold, how does it change? This is very important to understand. Now, let us try to understand heat transfer is basically doing what? Heat transfer is helping in the solidification. So, heat transfer will definitely control the cast structure. So, let us try to understand how the cast structure is evolving, what is the cast structure, what is the shape, size of the cast structure. These alloying elements, in steel you have lot of alloying elements, you may have carbon, you may have sulfur, phosphorus, silicon, manganese, other alloying elements. All alloying elements, because of segregation, they are rejected from solid to liquid. This issue I will take up in more details later on. Let us try to understand these alloying elements are rejected from solid to liquid during solidification. All alloying elements are rejected. There is no alloying element which will be more in solid and less in liquid, the concentration, it never happens. So, all alloying elements are rejected from solid to liquid. The solid will have solubility, less solubility for all alloying elements. The solid will be having less concentration of the alloying elements, and liquid will be having more. So, it is getting rejected as the solidification progresses. So, liquid is becoming more and more rich in the alloying elements. So, this is what I am telling, segregation makes liquid rich with solutes. So, what is the implication of this? Implication is the liquid steel which is adjacent to the solidification front, which is the temperature of the liquid is slightly lower. Because of what? Because it has become rich in the solutes. So, the solidification temperature is lowered because of this, and because of this we call it constitutional supercooling, because it is supercooling is happening not because of heat transfer, but because of segregation. So, whenever supercooling is happening because of constitutional supercooling it is called constitutional supercooling, because this supercooling basically means the temperature of the liquid adjacent just in front of the solid liquid front, solid surface is getting cooled because of segregation. So, this is called constitutional supercooling. But because of this, the solidification front, which was initially a plain front, it changes into dendrite. This is very important. Why dendrite forms? Dendrite forms if you have a single pure element, if you are solidifying it, you will not have dendrite. You will have a plain solidification front. Dendrite is occurring or forming because of segregation. Please try to remember, because there is segregation, there will be constitutional supercooling, and because of this you have dendrite, that means tree like formation, in a particular direction it will grow. So, this is important to understand. Then initially these dendrites are growing in specific primary direction. In which direction it will grow? It will try to grow in the direction wherever there is a heat transfer, number 1. Number 2, in the crystal, the direction, typical directions are say 1, 0, 0, in those directions this dendrites will grow. in cubic crystals. So, these initial dendrites grow in specific primary direction, subsequently you have secondary and tertiary dendrites along other directions. So, you have primary dendrites which are more long, and then you have at almost at their perpendicular surface direction you have secondary dendrites, and again to the perpendicular of the secondary dendrites you have some tertiary dendrites. So, this is very important to understand why you have solidification through dendrites, because you have segregation, because we are casting alloy, we are not casting a single element, the solidification is taking place of an alloy. So, there are a lot of solutes in it, all those solutes are enriching the liquid. Because of this, the solidification temperature of the liquid is coming down, it is becoming relatively cool. So, it is called constitutional supercooling, and because of constitutional supercooling you have a dendritic solidification front and not a plane front. It starts with a plane front solidification, but immediately gets into a dendritic form. So, dendrites start shooting out from the solidification front, and as I have told, initially dendrites grow in specific primary direction, and subsequently you have secondary and tertiary dendrites. Now, please try to understand what is happening during solidification. You have a solid shell which has solidified, you of course have liquid from which the solid shell is forming, and then you have a mushy zone. What is mushy zone? It is a combination of solid plus liquid. The portion of the liquid which has already got solidified, so this is the 100% solid. So, here the fraction of solid is 100, in the liquid the fraction of solid is 0, and in between in the mushy zone you have intermediate. That means, from 0 fraction of solid you are going to 100% of solid during solidification, and in between you have a mushy zone. It is called mushy because you have solid liquid both. This is very important. This mushy zone will dictate quality of the solid shell which is forming. So, we have to deal with it in a greater detail subsequently. So, please try to remember, during solidification, once solidification is over you have only solid, before solidification you have only liquid, but during the stage of solidification you have 3 areas: solid shell, mushy zone, liquid pool. Now, another thing I have mentioned here, what is the macrostructure of the whole solid? That means, when solidification is complete you have only solid. So, you have columnar zone, this dendritic columnar zone at the surface, and then central equiax zone at the interior. Why this forms? There are different reasons, but initially, as I have told, solidification you have columnar. Some people tell at the very instance of initial solidification there may be certain equiax zone at the surface which is called a chill zone. So, basically there is chill zone, but which is very narrow. So, virtually after this chill zone you have columnar. So, sometimes the chill zone you cannot even see, it is so narrow. So, basically you have 2 broad zones, one is the columnar, that means the dendrites in columnar fashion, growing in a columnar fashion, they call columnar zone at the surface, and finally in the equiax they are also dendrites, but they are equiaxed. Here it is columnar, the difference is between the shape of the dendrites. Now, how much is percentage equiax, how much is columnar in a cast structure is dictated by superheat and use of electromagnetic studying. You know superheat, because what is superheat? Superheat basically the difference between the actual liquid temperature during casting and the your melting point, the liquidus temperature. So, normally it is slightly higher than the liquidus, so that it is called the superheat. Now, the last session I have talked about this superheat because in connection with cleanliness of the cast structure I had talked about. If super heat is very low, then cleanliness is slightly affected, but if the super heat is low, you have mode of equiax zone rather than columnar zone, which is desirable is columnar should be less, mode of equiax should be there. Equiax means directionality of the properties are not there during rolling and during processing, things will be better to roll, easier to roll, there will not be any crack formation, but if you have columnar, there is a possibility of quality issues during hot rolling. So, lower superheat helps in having less columnar and more equiax, number one. Another thing is electromagnetic stirring. What is electromagnetic stirring? Normally when casting is taking place, the liquid steel is not stirred, liquid steel is stable, but you can start the liquid steel using some stirrer during continuous casting. When the solidification is has not got completed, that means it has started, it has not completed, then there is some liquid. So, that liquid if it is stirred, you get finer structure, you get finer grains, finer solid grains, fine. So, you have got more of aqueous grains, less of columnar grains. So, low superheat and electromagnetic stirring, these two are useful for having relatively more equiaxed and less of columnar. As I was discussing, when solidification is taking place, what is happening? You have a solid shell, this is the mold. So, you are going away from the mold. So, you have a solid shell, you have a mushy zone, you have liquid. So, liquid is naturally away from the mold. So, heat is getting transferred from the liquid into the mold, solidification is taking place, is not complete. So, solid shell, mushy zone and the liquid. So, here solid fraction Fs is 1 or 100%, at the liquid front it is 0, in between you have some solid fraction. So, this is the 0.5 line just to indicate what is the 50% solidification front. So, this what is the relative thickness of the solid and the mushy zone is dictated by, here I have shown the temperature. This issue I will be taking up later on just to indicate what is during the time of solidification, what is the relative thickness of solid shell and the mushy zone. In certain grades you have during the time of solidification thick solid shell and thin mushy zone, but in certain grades you have thin solid shell and wide mushy zone where you have more problem. So, it is dictated by what? Please try to look at these temperatures. This is T0 is the temperature on the solid shell. So, temperature, surface temperature which is very low, maybe 50 degree centigrade, 100 degree centigrade. The solid which has become solid long back and it is getting cooled also, so it is relatively less, maybe 100, 200, whatever it is. This is what is this temperature? When the solidification starts, this is the actual solidus temperature, not equilibrium. I have given you here the actual solidus temperature TSA. So, this point corresponds to actual solidus temperature. What is this temperature? This is TL, that means liquidus temperature. So, the difference between the liquidus temperature and actual solidus temperature will dictate what is the mushy zone depth. Lower the actual solidus temperature, more wide will be the mushy zone. That is why segregation plays so important role. What segregation is doing? More the segregation, more is the more depression is the solidus temperature, because the solidus temperature will be more depressed, more is the segregation. So, the role of segregation is to depress the solidus temperature. Why I have discussed this later, because the liquid which is solidifying subsequently later on is getting more and more rich in the solutes. So, the solidus temperature is getting more and more suppressed or depressed. So, what is happening? The gap between the liquidus and the solidus is increasing. If this gap increases, this gap increases, then the depth of the marshy zone also will increase. Please try to remember this. The whole idea of showing this is to drive home the point that the marshy zone thickness and the solid shell thickness when solidification is taking place is dictated by the liquidus temperature and the actual solidus temperature. I have shown here solid shell thickness, it depends on, related to the actual solidus minus the surface temperature. Marshy zone depth related to the difference between the liquidus and the actual solidus. So, what is segregation doing? Segregation is depressing the actual solidus. By depressing the actual solidus, this TSA is coming down. That means the difference between TL and TSA is increasing. So, more is the difference, marshy zone become more deep and solid shell becomes more thin. That means at the time of solidification you have thin solid shell, wide marshy zone because of segregation. And now this segregation, when I discuss segregation it will be more clear to you. This segregation depends on, the extent of segregation depends on the solute elements like sulfur, phosphorus, boron. These elements, they create more of segregation. The reason is known because the K value, the distribution coefficient is very low for these elements. Not only that, this distribution coefficient is also different between delta and gamma. That means how solidification takes place also influence the level of segregation. So, that will also influence the level of this change in actual solidus. So, that will also influence the depth of marshy zone. The marshy zone will be increased or decreased, solid shell will be increased or decreased, depends on that. So, these are very important issues to remember. So, let me discuss another important issue, that with heat transfer, I have told that with heat transfer the dendrite size, the size of the cast structures, so cast dendrites, they changes. How does it change? Say solidification, you are starting the solidification. I have told you at the start of the solidification relatively heat transfer is relatively high. Heat transfer is high means what is going to happen? The dendrite which is forming, they are relatively of a particular size. When you are going to, that means that the surface is relatively finer dendrites. When you are going to inside, that means that heat transfer, as you are going inside means what? The heat transfer is changing with time, solidification time, heat transfer is increasing, heat transfer is rather decreasing, that means heat transfer is becoming more and more slow. So, the size of the dendrites also will increase. So, this is the actual measurement. This is measured, this is dot ones, and this is calculated. This through modeling one has calculated. So, what is happening? So, dendrite size are, secondary dendrite size are say 10 micron at the surface, and after a time of say 10 seconds or let us say at a shell thickness of say 10 millimeter, you will find dendrites are say about 50 millimeter. So, you see this is a log scale. So, see what is happening at surface, dendrites are quite fine, 10 millimeter, 10 micron, sorry, 10 micron in size, and at a depth of say 10 millimeter, that means after a solidification time of 10 seconds, what is happening? It is increasing to as high as 50 to 60 micron. So, the dendrite spacing, that means this is secondary dendrites. Normally, it is the secondary dendrites or spacings are measured to understand what is the dendrite size, not the primary dendrites. So, this is dendrite spacing has been plotted, lambda is a dendrite spacing in the micrometer, and this way this horizontal surface is either the time or time is related to the shell thickness. I have told you earlier how time and shell thickness are related. So, as you are increasing the solidification time, that means as you are increasing the shell thickness, that means you are going more inside the cast product, your dendrites are becoming more coarse. So, please remember, higher cooling rate at surface results in finer dendrite spacing. Inside the casting you have relatively coarse dendrites because your heat transfer is relatively less there. So, this is another important thing to remember, that in a cast product, first it is a you have to near the surface columnar zone, and then only at the interior only you have equiax zone. But not only that, even the columnar dendrites which are forming, they are not uniform in size. You have relatively finer dendrites at the surface, and as you are going inside you have relatively coarse dendrite, which is this is because of heat transferred only. So, the heat transfer at the surface is less, or sorry, heat transfer at the surface is more, that is why you have this means higher cooling rate, higher heat transfer, you have finer dendrite. Inside heat transfer is decreasing, so you have coarser dendrite. Okay. Next session I will again talk about some other issues, maybe the effect of chemistry, effect of segregation and other related issues. Thank you very much.